Okay, so in the previous video, we learned the basic structure of statistical inference. So we learned that we are making a guess about the population using the sample, which is observed. Population is not observed, but sample is observed. And then from that, and a parameter is based on the population and which serves as the target of our inference. We would like to hit that target, that is the parameter. The other side is the statistic, which we calculate from the sample, right? So you may think the statistics is an estimator. Okay, then let's think about in more detail. What in those examples, one of them cannot be a parameter. So when I say parameter is the target of an inference, it sounds obvious, but what's more helpful is to think about what cannot be a parameter. So think about this like A. You'd like to estimate. So this is a parameter. If you assume it is a parameter, you would like to estimate the standard deviation of life expectancy of say like U.S. Adults in the United States. B, you'd like to estimate the expected increase in sales after a price cut of your company's commodity. C, total number of heads. You'd like to estimate the total number of heads when you toss 10 coins, right? It's obvious. D, you'd like to estimate the difference in mean gas prices in New York and California. And finally, you'd like to estimate the conditional probability of making a second free throw after making the first free throw in basketball. So, like I gave you 5 totally different estimation problems, but actually one of the estimation problem is not correctly specified. One of them is not a parameter, cannot be a parameter. What is that? Think about that. Okay, it's just brain teaser. The answer is C. Because total number of heads when you toss 10 coins, it's already finite observation. So this is not a parameter. This is a statistic. You observe the 10 coins, so this cannot be a population. And also, it is random. Like sometimes you may have one head, or other times you may have all 10 heads. So it's like target is not fixed, and it is not about the population. So it is now. Now you see it's more clear. To be a target, to be a parameter for statistical inference, first the parameter must be non-random. Of course, if the parameter changes when it changes for each experiment, when you repeat the experiment, if the parameter should not change, so that you can guess it. And like you may understand it this way, you can calculate this only when the sample size is infinity. Only when you observe infinite number of observations, the parameter is known. But it is unknown because we could not observe infinite sample, right? In that sense, again, going back to this case, tossing 10 coins is not infinity. It's just a finite sample. Or if you had to change it, like not just total number of heads, but expected number of heads, if you said expected number of heads when you toss 10 coins, then that makes more sense. That is a parameter. But just the number of heads is random, so it cannot be a parameter. But all the other guys say standard deviation of life expectancy. If you could observe all people's like longevity, then you can calculate that, right? And expected increase in sales after price cut. If you could do infinite repetitions of experiment like this, then you know the exact value of this expectation of the increase. Of course, the experiment is not possible, so that's why you don't know this. So you need a sample, a finite sample inference. And mean gas price, the same thing. Like if you could observe all gas stations in New York and California, you can calculate their mean gas prices, and of course then it is easy to calculate the difference. And conditional probability of the free throws. If you observe infinite number of free throws, then the conditional probability is known. But you only observe finite number of free throws. Of course, even though that is large, but still it's finite. So, as I said, the point here is it must be non-random, and the parameter must define the population. You have to think about in terms of the population. It must be able to be calculated. It must be calculated from the population. Okay, parameter is more clear. So you set, suppose now you set the parameter, and for example, for simplicity, we will consider the parameter is the expected value of a random variable x. So you want to estimate the mean. That is your parameter, your estimation problem. And then the next question is, how would you estimate that? So it's like I'm asking you, what is the mean of x? And you have to say something based on the data. But of course, this is a very simple example. So you know that the sample mean would be the natural estimator. Yes, right? But think about this. Sample mean is one possible way to answer that question. Or you could think about this. What about the sample mean after deleting the minimum and the maximum? You know, this kind of sample, like in the Olympics, this kind of calculation in the Olympics, right? It makes some sense. You are deleting the minimum and maximum because they are extreme values. Or you may use the sample median. In some cases, the median equals the mean. So some cases, the sample median could do the job, right? So what I want to tell you here is, when I ask you a question, you may answer it in a very different ways. There are various ways to answer the question. But what we need to study is, we are going to define what is a good estimator, and then we will find how to implement that. That is what you're going to do. And in other words, so whatever that can answer the question can be your estimator. So for example, if someone asks me what is the mean gas price in Albany, then I can simply, without even looking at the data, I can say $4. There is no evidence. I just chose a random number. Or I could say $10 per gallon. So it is extremely unlikely to be right, unlikely to be correct, but anyhow, I'm answering something. I did answer the question. So then it is one estimator. It is a bad estimator, right? So that's how we are going to study in here. Okay, right? So an estimator is any statistic, whatever statistic you use to estimate a parameter, right? Just like now the next question is, what is good, right? So again, same example. Suppose that you want to estimate the mean gas price in New York City, and you observe 100 gas stations, say they are random sample, and then which one you cannot use as an estimator. So suppose that you have 100 observations, but like it's up to you whether how you use the those numbers. So think about this. There are 5 different like researchers answering to this question. First, any number came to your mind, such as $10 per gallon, like I said. Like say, researcher number 1, researcher A said this way, and researcher B, half of the sample average, calculate this way. So X bar is the average of 100 observations, and somehow you divide it by 2, say by mistake. And C misunderstood the question and calculated the sample variance. And then, like, you can calculate sample variance of this 100 observations. And D, the population mean of the gas price in New York City. And E, just choose the gas price at the nearest gas station. So obviously all of these 5 answers are absurd. But first I'm going to rule out something that cannot be an estimator at all. One of them cannot be an estimator at all. Guess it. The answer is D. D is because population mean is exactly what we want to know. You cannot calculate the population mean because you do not observe it. It cannot be an estimator. So for example, $10 per gallon. As I said, it's unlikely to be correct, but anyhow, you are answering to the question. You are giving an answer even if it's wrong. And here, half of the sample average. Again, it's wrong. It will be wrong because you divide it by 2. But anyhow, you are answering. Variance. You calculated the variance, not the mean. It would be wrong, but anyhow, you are saying something. So, and finally, the gas price at the nearest gas station. Also, it is absurd. There is no reason to do this way, but you are answering to the question. So A, B, C, E are some kind of estimator because that is a guess, right? Just the problem is they are likely to be wrong. However, population mean is, it's just saying the same thing. I'm asking you what is the population mean. Then your answer is population mean. It is not an answer. You are not answering to my question. So D cannot be an estimator. It is unknown. You cannot calculate it. You must give me something that can be calculated from something or tangible number, actual number. Okay, so then as I said, we only allow a statistic to be an estimator. An estimator must be a number, actual number that you can calculate. And then from now on, we have to argue that these are all wrong. But why are they wrong? We have to make statistical statements about that. We will develop statistical rationale or statistical criteria why they are wrong, and then or equivalently to criteria why what kind of estimators are good. So we are going to do that in the next video. So in this video, we learned what cannot be an parameter and what cannot be an estimator. So again, estimation is to guess the parameter using an estimator. So first, we have to think about what can do the job, right? And then next, in the next video, we will discuss how do the job well. Okay? Okay, then see you in the next video. Bye.